All right, so I just wanted to go through these conceptual questions and problem before the weekend so that you could check your work. Hopefully you did look at them, um, the ones that we didn't get time to go over in class. Okay, so our first question is the concept question. It says a player kicks a ball in a high arc toward the opponent's goal. When the soccer reaches its maximum height, how does the speed compare to its initial speed? We're going to assume that air resistance is negligible. So let's just draw a picture of what we think maybe the projectile motion would look like. So here is a sketch of maybe how the soccer ball might go. The initial kick sends it at an angle of theta measured to the horizontal. It has some sort of v initial speed. And if we break down those velocities into components, v naught y is equal to v naught times the sine of theta, and v naught x is equal to v naught cosine theta. Remember that what's going to happen is as the object goes up into its path, the Vy is going to decrease due to gravity because Vy is equal to V naught y minus gt. And at the very top of its flight, Vy is equal to 0 and Vx is just equal to its initial V naught x because that didn't change at all because there is no acceleration in the x direction. The speed is just the magnitude of the velocity, which would be looking at the x component and the y component and taking the square root of the sum of their squares. So what happens is its initial speed is the v naught, but its speed at the top is just the v naught x. So the speed at the highest point is going to be less than the initial speed because of that. Here's another question. It's similar to some things that we've seen before. If we have a plane, so I'm going to draw a very sad little plane because that's all that I can do. And it's going in a constant speed, so I'll just call that V naught, at a constant altitude. And then something's going to be dropped out. So the object that's dropped has a V naught x initial equal to V naught because of the fact that it was traveling with a plane, and so it's going to continue. It has that initial velocity because it was moving with the plane and then it was just dropped. It wasn't propelled in any certain way. So the object that's dropped is actually, again, has this initial velocity of V naught. And as it falls, that object, I'm going to just draw it down here, is going to kind of go in a parabolic path, retaining its Vx, and then fall. But because the plane is also moving horizontally with the V naught, the plane is always going to be right on top or above the falling object. So the object is going to remain directly under the airplane. And this is a case where, of course, this is true because we're assuming there's no air resistance. Okay, so here is objects that are launched from the ground, and we want to talk about when they hit the ground. So we have to ask ourselves what determines their time of flight, which is the amount of time that they're in the air. It basically is going to be determined by the maximum height they rise to, because they're all going to be undergoing, the same y motion. Their x motion is going to be different, but the ones that go the highest are going to be in the air the longest. And so if we want to talk about which one is going to hit the ground first, it's going to be the one that has the smallest height. So we want to go from smallest height to highest height. And so the lowest is C, then I go to B, then I go to E, then I go to A, and then I go to D. Again, what we've used in this case is the fact that the one that goes the highest is going to be in the air the longest, because that will determine its time of flight. Now we can kind of use this to answer this question. So we have a destroyer firing 2 shells with the same initial speed at 2 different enemy ships. And we want to know which one is going to hit first. Again, the one that has the higher time of flight will go higher. And so this one takes longer, and then this one will hit first. So enemy 2 will get hit first. This is actually, sometimes there's a problem posed as a physics problem. It's called the snowball fight strategy, where if you're in a snowball fight, you could launch a snowball up really high in the air, and then the person you're throwing it at is going to be watching it. And then as they're watching it, you throw one at a lower height, like kind of buzz it right towards them, and then they're going to get hit because they're distracted. So next time you're in a snowball fight, remember that. And then finally, we have a man on a building throwing a rock with a speed of 30 meters per second and an angle 33 degrees above the horizontal. And we want to find the maximum height, the speed of the rock just before it hits the ground, and the horizontal range. I actually realized once I looked at this, it's super similar to the example problem that I already posted for an example of an LO problem. But let's just see. This would be a good one for you to try on your own to see if you kind of understood what I was saying in that example problem. And so we know that this object is going to go like up like this, dun 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 dun, and finally hit the ground. So some of the things we're interested in is this range, and we want to know V here, and then we also want to know this height. Those are the questions. Our equations for this particular problem is x is equal to v naught cosine theta t, so that's equal to 30 cosine of 33 t. Y is equal to, I'm going to say that this is y equals 0, so y naught is 15 plus 30 sine of 33t minus 4.9 t squared. Vy is equal to 30 sine 33 minus 9.8 t. So the first part is to find the highest height. We use that Vy is equal to 0 at that time. So Vy is equal to 0 is equal to 30 sine of 33 minus 9.8 t. So t is going to be the 30 sine of 33 divided by 9.8, and I find a time of 1.66 seconds. I'll use that in my y equation. Oops. I got a y of equal to it's going to be 28.6 meters, but keep in mind I want to find h. H is equal to that y minus the 15 that it was at initially. So I find that 13.6 meters. So this is the height that it rises to above the top of the building. And so again, remember that I said that this y is equal to 15 plus h because of my initial y position. And so I had to subtract the 15 to find that maximum height. Now let's find the speed of the rock just before it hits the ground and the horizontal range. Both of these mean that I need to find the time of flight. And so I need to find the amount of time it's in the air. I know when it hits the ground, y equals 0. So I'm going to use that. Y equals 0 is equal to 15 plus 30 sine of 33 times t minus 4.9 t squared. So this is a quadratic equation that I solve. And I have to use a time that's greater than 0. I find that time is equal to 4.077. Now, my Vx is just going to be equal to my V naught x, which was 30 cosine of 33, and that was equal to 25.2 meters per second. Because I want to find the speed when it hits the ground, I'm actually going to need to find Vx and Vy. Notice my Vy when it hits the ground is minus 23.7. It has to be negative because it's coming down. V, the speed, is the square root of the two components squared, and that turns out to be 34.6 meters per second. It just asks for the speed, so I don't need to find the angle. And then the range is going to be equal to the x value at that time, which would be V naught cosine of 33 times the 4.07. V naught was, I don't know why I didn't put it in there, it's 30. And I get a range of 102.7 meters. All right, so hopefully this helps you. You should do the questions and the problems on your own, and then you can use this video. Hopefully you're using it to check your work.